Okay, I think we can start the seminar. Thank you for coming. Today we have Michael Abdul-Masih. He's originally from the USA, where he completed both his bachelor's and master's degrees. In 2016, he completed his PhD in astronomy in Leuven in May of 2020. And from there, he did a postdoctoral fellow in ISO, Chile. In December 2023, he began as a La Caixa Junior Leader Fellow at the IAC, and in September of this year, he will start as a Ramon y Cajal Fellow at the ULL. And he's going to be presenting his seminar about massive overcontact binaries today. Thank you.
Well, thank you. Yeah, I'll take this. Can you guys hear me if I talk here like this? And if I talk like this, no? Maybe? Okay. I'll keep this in my hand in case I turn around. So thank you very much to the Seminar Commission for inviting me to give the talk today. As Alba mentioned, my name is Michael Abdul-Masih, and one of the main lines of research that I have been investigating over the past 10 years of my time in astronomy has to do with massive overcontact binaries. And these are binaries that have this kind of strange shape that you see here, where you have two stars that are so close and so close to one another that they are actually sharing material between them through this common envelope that you see here. Now, this is a very important phase in massive star evolution, and today I hope to kind of explain to you why it's important, why we should be interested in this phase, and what it can tell us about the evolution of massive stars in general. Okay. So before we start, I think it's important to define our terms. Depending on who you talk to, the term massive can mean very different things. When I'm talking about massive stars, I'm talking about stars that are more than 8 times the mass of the sun. So these are stars that will end their lives via core collapse. And they're characterized by having very strong stellar winds, very high UV fluxes. And because of these two, they can drive the chemical and mechanical evolution of their host environments. So here, for example, you have a beautiful example of this. This is the Bubble Nebula. And this is the effect of a massive star in action and how it's shaping its environment. We can't really talk about massive stars without talking about binarity. We think, as of right now, that all massive stars will be born in a binary system or higher order multiple. And about 70% of these are expected to interact with their companion at some point during their lives. And the presence of a second object can have a huge impact on the evolution of each of the stars in that system. And binary interactions and binary evolution allows us to reach end products that wouldn't be possible with single star evolution. And today, we're going to be kind of focusing on this piece of the pie down here, this 24% of stars that we expect to merge at some point during their lives. And specifically, I'm going to be talking about massive overcontact binaries. And these contact binaries, this is the phase that happens directly before the merger. So this is as far along as you can get where you have your two separate stars, and then after that, they merge and crazy things happen. Now, when exactly that merger happens is still an open question, and there's still a lot of physics that we don't understand when it comes to this phase. So we know that about 24% of all stars should go through this phase at some point during their lives. And during this phase, you have many simultaneous physical processes that are happening. So for example, you have mass exchange through this bridge region where the stars are connecting and overlapping. You have tidal locking that force your stars to maintain their rapid rotation. You have mutual illumination. Both stars are irradiating one another. You have internal mixing, both within each star individually and then also across the bridge between the two stars. You have angular momentum loss via winds, etc. So there are many physical processes that are happening at the same time. And unfortunately, we don't have very strong constraints on a lot of these physical processes. And this is due to the fact that we don't have many of these stars that we can actually observe. And those that we can, the observational constraints is something that we need to work on. Now, this is important because when we talk about what results from a merger and what massive stars or what contact binaries are expected to form as end products, there are many different possibilities. Here I'm just showing one. So they've been proposed to be progenitors of magnetic massive stars. So here in this case, the magnetic field begins when the stars first come into contact due to shear between the accreting layer and the surface. And you start getting a modest magnetic field here. And then later, when the cores of the two stars merge, your magnetic field also is bolstered. In the same way, they've been predicted to form BE stars. So BE stars are very rapidly rotating B or O type stars that have a decretion disk of material that's forming around them. And this is also one expected endpoint of contact binaries. They can also form LBVs, luminous blue variables. They can form blue stragglers. And they've also been theorized as progenitors of gravitational wave sources. However, the physics that you need during the contact phase to lead to each of these end products is quite different. And as I mentioned up until this point, a lack of quantitative observational constraints means that in your models, you can tune that physics to different orders of magnitude and get completely different end products. So part of what I've been working on during my research is trying to better constrain these observational values so that we can better inform the models that we have for these systems. So if you look at this from kind of what we expect from theory, what the current picture looks like, there are three kind of main predictions that we get when you look at evolutionary and population synthesis models. So first, we expect the contact systems, we expect them to very quickly equalize in mass. So once they come into contact, we expect there to be rapid mass transfer from the more massive to the less massive star until they equalize. Next, we expect them to be stable on the nuclear timescale and eventually merge as equal mass systems. And we expect them to be fairly common. So here we expect there to be about 1% of all observed O-type stars. We expect there to be in a contact phase right now. The problem is that when you look at the observations, we only have about 25 massive contact systems that are currently known. And this is including both confirmed and unconfirmed sources. And there's been some work recently to expand that sample a little bit more. And I'll come back to what I mean by confirmed and unconfirmed in a little bit. So there seems to be some tension between the observations and the theory already, just by these numbers. And I'm hoping to kind of explain that a little bit more throughout this talk. So how do we actually detect and characterize these systems? The major features that we use to identify contact systems is both their photometric light curves and the radial velocity curves. So they have very short periods. We're talking about periods between 1 and 2 days. Some of them can get a little bit longer than that, but in general, that's kind of the period range that we're looking at. And if you look at their light curves, you get very large amplitude changes in their light curve as a function of time. So here, for example, you see about 0.2 change in the magnitude for this particular star. And this is actually this star here, which is VFTS 352. I have a 3D printed model of it because it's good for demonstrations. And this is a 30 plus 30 solar mass star. Now, if you look down at the radial velocity curve, you can see that the semi-amplitude of the radial velocity curve is about 300 kilometers per second. So we have very large radial velocity shifts, very large flux deviations across the orbit, which means that these should be the easiest binaries to detect. They have the largest radial velocity amplitudes because they're the closest binaries that we know of. And they also have very strong light curve variations. And on top of that, we can also see them at very low inclinations. Most eclipsing binaries, you need to see them almost edge on to actually detect the eclipse. With contact systems, because of their unique geometry, you can see them at very low inclinations. I think the lowest inclination contact system that we currently have is about 17 degrees. So this is really, really almost edge on. So what that means is that we should be able to detect them at much greater inclinations than most other binaries. And also due to their shape, it means that the light curve is constantly changing. You have a sinusoidal-like light curve with all of the contact systems in comparison with regular detached eclipsing binaries where you have a flat out of eclipse region and then sharp eclipses and then flat out of eclipse region. So if you're unlucky with a detached eclipsing binary, you could miss the eclipse entirely. But with the contact system, it's very difficult to not notice these very big variations. Now, I mentioned that we only have 13 that are confirmed and more that are kind of expected or predicted. And this comes back to how we actually characterize these systems. So here I'm plotting the light curve of a contact system in blue and a semi-detached system in green. And these are the two systems that I'm showing here. So you have the contact system up here at the top, then you have the semi-detached system just below. And these are very different configurations, and the physics that's happening during these phases are very different. But the light curves are almost exactly the same. So if you look at the radial velocity curve, though, this is where you can start to break this degeneracy that you have in the light curves. So when I'm talking about systems that are suspected and systems that are confirmed, I'm talking about systems that have been fit with both the light curve and the radial velocity curve simultaneously, because fitting just one or the other doesn't allow you to break this degeneracy with the geometry. So now if we consider how our current picture that I showed you in the beginning, they're expected to be fairly common. About 1% of all O-type stars should be contact systems, but they should be the easiest binaries to detect. So the fact that we have so few of them means that there must be something else going on. So now let's get into how we characterize them from a spectroscopic point of view. Traditionally, what you would do, and what's been done in the past, is that when you have a close binary system, the way that we would go about getting the parameters of each of the components is first we would disentangle the spectra. So we would separate the components, or the contributions of the primary and the secondary. Then we would fit each of those two systems individually and get your stellar parameters and abundances of your primary and the stellar parameters and abundances of your secondary. Unfortunately, going through this process, you impose several assumptions onto your system, which ends up making your system look very different in the end to what it looked like in the beginning. So here, for example, I'm showing how your temperature is distributed across the surface of your contact system. During the disentangling, you're making an assumption that the contribution to the spectrum is not changing as a function of phase, so that it is constant and spherical in the orbit. So what that means is that you're imposing a spherical assumption on your two stars. And then later when you do the atmosphere fitting, and here there are various ways that you can do this. Here I have the GA plus fastwind. GA is a genetic algorithm. Fastwind is an NLTE radiative transfer code that's appropriate for massive stars. Doing this atmosphere fitting, you fit each of these stars as if they were individual single stars without a companion. So now all of a sudden we've taken our contact system and approximated it as two single spherical stars without the effects of a companion. Unfortunately, these kinds of assumptions can make a huge impact on the parameters that you get out from your system. And I've spent a lot of time during my PhD trying to come up with a better way that we can tackle this problem. To do that, I came up with the SPAMS code, which is the spectroscopic patch model for massive stars. And the way this works is pretty much in 4 steps. So first, you generate a mesh that represents the 3D surface geometry of the star, following the Roche formalism, so Roche geometry. You populate the mesh with local conditions. So for example, your temperature, your local surface gravity, your local radial velocity of each individual point across the surface, etc. Then you assign individual fastwind models to each patch across the surface, and then you can integrate. And by doing this, you can account for things like the distorted geometry. You can also account for the temperature changes across the surface, as well as the broadening of your lines due to rotation and these other kinds of effects we get directly from this model. So once we do that, we can integrate over the visible surface and reproduce synthetic spectra for any given phase or orientation of any given binary that we'd like. And this allows us to, for example, model how your spectrum is changing as a function of time. So comparing this with the more traditional techniques, now we can avoid a lot of these assumptions that have gone that have limited our way to actually get the parameters out properly. So with this, we can directly fit both of the stellar components simultaneously, and we don't need to make any assumptions about disentangling or anything like that. We can get directly both the stellar and abundance parameters of both components. So now that we have our tools, we can actually get into the stellar and binary properties of massive contact systems. Arguably, what I would say are the 3 most important parameters that we have for for massive contact systems would be their periods, their mass ratios, so the Q that you have here, and their fill-out factor, which F. So as you can see here, most of your periods are between 1 and 2 days. You have a few stragglers. This guy down here is very weird. If you're curious about him, ask me, but I won't go into him right now. And the fill-out factor here is a measure of how filled out your star is. So what this means is if you think of the bridge of your contact system, it's a measure of pretty much how overlapped your two stars are. So if you have a fill-out factor of 1, this means that you're exactly filling your Roche lobes. So a fill-out factor of 1 would correspond with this red line here. A fill-out factor of 2 means that your system has expanded so much it's overflowing through your L2 Lagrange point. And once you start overflowing through L2, you very quickly lose mass from the system. Your two components very quickly merge, and that's pretty much the end of the evolution of your contact system. So you can kind of think of this fill-out factor as a proxy for the evolution of your system. Low fill-out factors are younger or have come into contact more recently, whereas high fill-out factors are stars that have come into contact longer ago. So you can kind of use a fill-out factor as a bit of a proxy for the evolution of your contact system. Now, one of the assumptions, or not the assumptions, one of the predictions that we have from population synthesis is that overcontact systems are expected to quickly equalize in mass. But if we look here, we have quite a lot of systems with mass ratios that are away from 1. So this is weird. If we look at the second kind of point that we have here, that they're expected to be stable on the nuclear timescale. If they're expected to be stable on the nuclear timescale and they're expected to very quickly equalize in mass, then we should not see so many systems with mass ratios away from 1. So this is another tension that we have between the observations and the theory, and this is something that we're still trying to better understand. So why do we find so many unequal mass systems? An interesting point here, if you consider the mass ratio versus fill-out factor plot, there are not so many points on here, but you may be able to convince yourself that there does appear to be a little bit of a trend where as you go to higher fill-out factors, your Q tends to go closer to 1. Maybe. We'll get back to that. So going back to the statistics of the sample, if we look at the spectral type distribution of the massive contact systems that we have, about 30% of them are B plus B, and 70% of them are O plus O. Now remember here, I'm only considering stars that are more than 8 solar masses. So this is B3 and above. So while there are many more B stars than there are O stars, the fact that we are cutting the B star regime quite high up, this is not an entirely unexpected statistics. But notably, there are no O plus B systems. Now this is weird because remember, we have quite a large range of mass ratios here when we look at these systems. So it's weird that we have no systems where you have an O star with a B star, considering that we have all of this mass ratio. So what's happening here? Well, if we look at some of these unequal mass systems, one thing that we notice is that despite the fact that, for example, you have a 26 and a 19 solar mass star, if you plot them on the HR diagram, they fall right next to each other. So here, for example, what I'm plotting is evolutionary tracks at various rotation rates. I'll come back to that in a second. For the system, fitted with both 1D techniques, the traditional method that I showed you before, and with SPAMs that accounts for the 3D geometry. And as you can see, whether you're fitting with 1D techniques or 3D techniques, both systems, the primary and the secondary, fall right next to each other on the HR diagram. Now, if we consider this 25 solar mass track, which is close enough to this 26 solar masses that we have here, the primary is more or less where it should be, but your secondary should be down here on your HR diagram. So there's some process that is tending to equalize the mass of, or equalizing the temperature of your systems. So there's some energy transfer or some heat transfer that currently we don't have implemented in our models. And there's been some work by Matthias Fabry, who's been looking into energy transfer to try to get a formalism for this. Another interesting point is that both components are overluminous. I mentioned that we have different rotation rates plotted here. Most contact systems in general have rotation rates of about 300 kilometers per second. So we can use this solid line as kind of a guide for the eye. So you would expect your two components to fall kind of close to around here-ish. On this solid line, but it's 26 solar masses instead of 25, so a little bit above. However, if we look at their locations on the HO diagram, we see that both components are higher than this. Having one component be overluminous is easy. When you have mass transfer, that's not unexpected. Having both components overluminous is difficult to do. And there are some kind of theories that we have about how this can happen. For example, if when the contact systems initially come into contact, they expel mass from the system. So if you started with a more massive contact system and then, sorry, a more massive binary and then expel mass from the system, this can allow you to get both components to be overluminous. But we still need to look into this a little bit more and better understand what's happening here. There's also been several studies in the past that have looked at the period change. And the period change is really interesting because it can tell you how quickly your mass is being transferred between your two systems. What we have found so far is that all of the contact systems that we've looked at are stable on the nuclear timescale. This means is that the mass transfer is very slow, it's evolving on the nuclear timescale. So we don't have this quick exchange of mass even for unequal mass systems. So going back to our slide that I had here a couple slides ago, if we then add in this new piece of evidence, we can kind of start to change our understandings a little bit. So, I mean, the expected to be stable in the nuclear timescale, that is true. They may be equalizing in mass. Again, as I mentioned, if you believe this trend here, there aren't too many points, so we need to fill it out more to make a strong statement here. But if you believe this trend, then you can say yes, that they may equalize in mass and that they may eventually emerge as equal mass systems. But it seems pretty clear that this is not happening quickly, that this is happening more on the nuclear timescale more than the thermal timescale, which is what was predicted. We can also talk about higher order multiplicity. So many of these stars are found in higher order multiples. And there have been several ways that we have found these systems to be in multiples. So, put that down for a second. A lot of these discoveries have been somewhat serendipitous. People have been looking to measure the period change, to measure the mass transfer rate, and they have found on top of the parabolic curve that you would expect for mass transfer, they've found an additional sinusoidal or cyclic feature on top. And this is actually coming from companion. What's happening here is what we call the light travel time effect. If you have your binary system in a triple, when your star is here in the orbit versus here in the orbit, when it's here, it's closer to you. It means that the light has less distance that it needs to travel, which means that if you measure the time that the eclipse happens, due to the travel time of the light, it happens earlier than if you were to measure it at this point in the orbit. So what this allows you to do is if you find this cyclic change in your expected, in your measured times of eclipses, then this is the indicative of a companion, an additional companion being present. So most of the triples that we have found have been through these light travel time effect. Now we've also found some through spectroscopy. For example, we have two that have been discovered as quadruples to be SB4s. Quite a nasty system. So this is actually a pair, the one that I'm showing here, is a pair of two massive close systems. So you have a contact binary and you have one that is very close to being semi-detached. And they're in a system. We've got no idea what the orbit of the quadruple is, but they're in orbit with one another. We also have two detections via interferometry, where distant companions have been found interferometrically. Putting everything together, we kind of, this is what the picture looks like. So right now, about 70% of our systems, of our confirmed contact systems, have at least one additional component, if not more. It's important to note that this 30% here of the lonely contact systems, is an upper limit. To get the time base that's required to detect the light travel time effect for the triple, a lot of the periods of those outer systems are on the order of tens of years. So if you don't have a long enough baseline, it's very difficult to detect those triples. For several of the contact systems that we have here, we just don't have enough data to say for sure one way or the other if it is a binary or a higher order multiple. So you should think of this 30% as an upper limit, and that it's possible that as we have more data for these systems, that more of them become triples or higher order multiples. Now, if we compare that with the statistics of the general population of O and B type stars in terms of their multiplicity, you can see that we're pretty much right in line with the triple. So here, the darker or the bolded crosses are binary fraction. Your lighter ones are your triple fraction, and your triple fraction here includes your triples plus your quadruples plus your quintuples plus over the total number of O-type stars in this case. So you can see that right now the triple fraction of the general population of O-type stars is about 70%. And without bias correcting our sample, we're already at 70%. Now, it is true that, for example, we are kind of biasing ourselves in the sense that we are selecting very close binaries, and that it is very likely that they will have extra companions. But this is still an interesting point. The fact that our triple statistics are so high may imply that triples are playing a role in the formation of these systems. And if our contact systems are limited by triple statistics instead of binary statistics, then this may play a role in why we have so few of them. Now, talking about the future evolution, what will happen with these systems? As I mentioned before, you have several different possible evolutionary outcomes. So the idea is, can we better understand what's happening during this phase to kind of inform us as to which of these end products are more likely or less likely than the others? So one kind of property that we can use to separate these a little bit, or at least isolate one of these pathways, is the internal mixing. So when you have very efficient internal mixing, you can form black hole binaries. If you have less efficient mixing, then you would get a merger on the main sequence, and then you could form some of these other end products. So how exactly does mixing play into this? What do I mean by mixing here, and how do you get mixing in massive stars? So if we take your traditional evolutionary picture of a single star, you can start with single stars. You start with your hydrogen-rich envelope and your helium-rich, as it evolves, it will get a helium-rich core. And then what happens is throughout the evolution, your core will shrink and your envelope will expand. And conservation of angular momentum tells you that your core will spin up and your envelope will spin down. Now, at the interface between your core and your envelope, this can lead to shear instabilities, which leads to eddies, which mix material locally between your envelope and your core. This would allow you to bring fresh material from the near core region of your envelope down into the core for additional material to burn, and will bring processed material from your core up to the near core region of your envelope. Another important effect comes from rotation, among other things. So if you have a rapidly rotating star, as your star is rotating, your envelope will bulge out, whereas your pole will stay the same. This is due to the centrifugal forces of your of rotation. And the changes in your radius will lead to a change in your surface gravity, which in turn leads to a change in your temperature across the surface. So you'll have a hotter pole and a cooler equator. In 1 second. And these temperature variations can lead to very interesting physics that happens. So your rapidly rotating stars can't be simultaneously in hydrostatic equilibrium and thermal equilibrium. Your star prefers to be in hydrostatic equilibrium. What that means is that your star is out of thermal equilibrium, and the star will try to get itself back to thermal equilibrium. And the way it does this is by large-scale flows throughout the envelope of the star. So what happens is if we look at the single star case, you will have material that flows up from the near core region up to the poles, then across the equator, across the surface down to the equator, and then from the cool equatorial region, it will go back into the envelope to the near core region of your star. Now, I've been talking about rotation, but I mean, of course, my presentation is about contact systems. And when you have a closed binary system, this can also affect these flows. In fact, these flows are originating because of changes in your geometry, the fact that you are not in spherical geometry. If you have a closed binary system, they're also they also don't have a spherical geometry. And as you have a close binary companion to your star, and as you start to deform your system, the geometry of the flows change quite a bit. So you no longer have these nice, neat flows that you have in the single star rapidly rotating case. In the binary case, your flows change by quite a bit. And actually, having the same rotation rate, but having a companion close by can boost the efficiency of your internal mixing by about twofold. So this really can make the mixing quite a bit stronger. So putting these two together, if we have ways of mixing between the core and the envelope and all the way throughout the envelope, then this is very interesting, because if the mixing is efficient enough, then essentially we can completely mix our entire star. And this is kind of the idea behind this concept here of chemically homogeneous evolution. If you have less efficient mixing, or I'll say in kind of the normal evolutionary pathway, what happens is that your star starts off homogeneous, but then your core will quickly form as it's burning. You will get your helium-rich core and your hydrogen-rich envelope, and then you'll have the contracting of the core, the expanding of the envelope as the star evolves. Now, if you have very efficient mixing, what happens is that you can prevent this chemical gradient from forming. So instead of having a well-defined core and an envelope, you have a star that is chemically homogeneous, which means that the star can completely burn all of the available material throughout the star. So there are several consequences of this. For one, the lifetime of your star can be extended by quite a bit because you're expanding the reservoir of burnable material. Another interesting consequence of this is that without a well-defined core and envelope, instead of expanding as the star evolves, the whole star ends up actually shrinking. And this is very interesting if you consider this in the context of massive contact binaries. The great thing here is that they are tidally locked, so you can maintain the rapid rotation throughout the entirety of their lifetimes. So even though a single star will lose angular momentum due to the winds, in contact binaries, the angular momentum of your orbit itself maintains this high rotation rate throughout the entirety of their lives. If your systems are evolving via the chemically homogeneous evolution pathway, then what this means is that having your contact binary, you have your two stars very close to each other, and if they end up shrinking within their Roche lobes instead of expanding, then they can actually detach and collapse directly into black holes right next to one another, allowing you to form black hole binaries with periods of a few days. And these are close enough that they can merge in a Hubble time. So this has been theorized as a potential pathway to form gravitational waves, and it may account for up to about 70% of the gravitational wave detections from isolated binaries. So how do we actually look for evidence of this internal mixing? Well, the idea is to look for processed material from the core on the surface. Now, in massive stars, you have hydrogen burning into helium via the CNO cycle. Now, this is a catalytic cycle that pretty much takes your carbon, converting it into nitrogen, back to carbon, into nitrogen, over to oxygen, to nitrogen, back to carbon, etc. It's a catalytic cycle. And through here, you put in some hydrogen and you get out a helium. Now, this particular reaction down here is the slowest reaction of this cycle. And what that means is that you get a buildup of nitrogen because you're building up nitrogen faster than you can process it. Your nitrogen abundance will increase. What this means, because this is a catalytic cycle, the total number of nitrogen, carbon, and oxygen isn't changing. So if your nitrogen abundance is increasing, then your carbon and oxygen abundance are decreasing. And as well, you're getting a higher abundance of helium in your core because you're burning your hydrogen into helium. Now, mixing should also lead to changes in your surface temperature. Your surface temperature should be higher when you have efficient mixing. Putting this together, we can detect both of these via spectroscopy. So now, doing so, it doesn't seem to work. So here what I'm showing is your carbon abundance, your nitrogen abundance, and your oxygen abundance as a function of age for various rotation rates. So here you have a rotation rate of 0, a rotation rate of 165. This 322 is the closest one to the canonical 300 kilometers per second that they're rotating at. And then you have 400 and 500. Now, we can use these rotation rates as a proxy for the efficiency of the mixing. These are single star tracks. We're, of course, dealing with binaries. So we would expect is that even though they're rotating at 300 kilometers per second, due to the extra mixing in the envelope from the Eddington-Sweets, perhaps these values should be, they should correspond more with the 400 or 500 kilometer per second track. What we find, however, is that both with the 1D and the 3D techniques, we don't find any evidence that these stars are processed in CNO at all. And this is consistent throughout the samples that have been looked at so far. So this is weird. We don't seem to be seeing evidence of this internal mixing from the chemistry. Now, if we look at the temperatures, you do. The temperatures of your components are hotter than you would expect them to be. And I kind of mentioned this before, earlier in the talk, where I mentioned that both components of this system, this is the one that we looked at before, are overluminous. And we can see this with other systems as well. So for example, if we look at this 30 plus 30 solar mass system, which is this guy that I have over here, we can see that both the primary and the secondary seem to be following this 500 kilometer per second track. Again, indicating that there is extra mixing happening in the system. Same thing over here, we have a 17 plus a 14. It seems to be, especially if you look at the fits with 3D, it seems to be much above the temperature that we would expect for these systems. So this is kind of strange because your temperatures do seem to be showing evidence for additional mixing. So what's happening here? We kind of have a conflict between the chemistry and the temperatures. And this is still very much an open question that we are trying to understand. So coming back to the future evolution, in terms of the chemistry, it's kind of difficult to say. The chemistry doesn't seem to be showing any evidence for this extra mixing. So, I mean, if we can say that the stars are not chemically homogeneously evolving, then we can say with a bit of confidence that they probably won't form black holes. That's about all that we can say. And this is still kind of a shaky conclusion because the temperatures do seem to be showing evidence for this. What we can say, though, is looking at the period changes. The period changes indicate that the systems are stable on a nuclear timescale. So they should be there. We should be able to find them. If they are around, then they should be around for quite a while. Triple interactions could become important both for the formation and also the future evolution. So if chemically homogeneous evolution does work, and we do form a black hole binary, having a close triple companion may allow you to force the black hole binary closer together and merge within a Hubble time where a regular binary black hole system may not. But going into a little bit about the formation, and I mentioned this before, if we are limited by the statistics of triples, then this may allow us to better understand why we have so few of these systems. So let's do a bit of a thought experiment and kind of put several pieces that I've talked about together. So if you have an initial binary that's a little bit farther apart, and you have a triple that's a little bit closer than what we find it now, the triple interactions with the inner binary systems will cause your binary to slowly migrate towards one another. What happens is when the system comes into contact, we expect it to expel some mass. So remember, we found both components to be overluminous, and one way that we can do that is if you lose mass from the system. So if your inner component is losing mass, then what happens is that your triple will move farther away. And that may explain why kind of the picture that we have now, where we have contact systems and triples that are in a period that's a little bit farther than what you would expect for triple interactions to be important right now. But if they were closer in the past, then this may be able to explain some of this. Now, I've kind of mentioned this throughout the talk, but we have several tensions between the theoretical predictions and the observational constraints. So the total number of systems is far below expectations. We're still trying to figure out why this is the case. And we've made some progress in this. We have some ideas, but we don't have any solid conclusions. So we have several avenues that we can explore, which is exciting. The distribution of mass ratios is much flatter than expected. So it seems that these systems are not equalizing in mass quickly. They may be equalizing in mass over the nuclear timescale. But again, we only have 13 systems that are confirmed. So it's difficult to make very strong statements in this direction. Internal mixing does not appear to be as efficient as initially expected. If we consider again this triple channel, if your stars initially start out a little bit farther apart and they aren't rotating as rapidly, then perhaps the chemical gradients can form before the stars actually come into contact. And if the chemical gradient has formed and then they spin up, once the chemical gradient is formed, it's very difficult to mix across that. So that may allow us to explain these higher temperatures and the chemistry. But again, this is something that we need to look into and better understand whether or not the physics of this channel is possible or not. In terms of future prospects, with the large amounts of surveys that are coming up, hopefully we will be finding many more of these systems, hopefully. And hopefully we'll be able to start actually making statistical arguments instead of going system by system. We also have the tools to allow us to spectroscopically analyze these systems with fewer assumptions. So we can actually start going through the sample and systematically analyzing all of these systems. We need to better understand how what role the triples play in the evolution here, both in the formation and also the future evolution of these systems, whether they do have an effect, whether they're just they're not affecting anything, or whether they're actually driving the evolution in some way. I didn't go into this too much, but the surface temperature distribution remains an open question. If you change the distribution of the temperature across your surface, then this can change the geometry that you get out of your contact system. If you say that the temperature is more strongly correlated to the surface gravity, then that changes your geometry that you need to reproduce the same light curves. That's also something that we can look into, and this is something that interferometry can help us with. So it's also a very interesting prospect. Now, Alba mentioned that I'll be starting my Ramon y Cajal in September, and actually my Ramon y Cajal is focused on these two first points. Looking through the test database and taking a sample of 4,000 O-type stars, I've identified about 125 very promising close massive binaries. I hope that several of these will end up turning into confirmed contact binaries. And my project focuses on combining this test data with follow-up spectroscopic data that I have obtained from both the Hermes telescope, the Hermes instrument on the Mercator telescope in La Palma, and UVES from the south. So I have 4 proposals that have gone through. So I have all of the data coming, wrapping up just about now, just in time for me to start. And the idea is to do both the confirmation of their geometries by fitting both the light curves and the radial velocity curve simultaneously, and then later doing the atmosphere analysis by analyzing the spectra of all of the systems. And hopefully this will allow us to kind of be able to fill in these plots with a little bit more detail and make some stronger conclusions than we've been able to make up to this point. So I will leave my summary up here. It's everything that we've been talking about. So thank you very much for your attention, and I'm happy to take any questions that you have. I didn't end up using any.
Okay, thank you very much, Michael. Are there any questions in the room or online?
Hi, Michael. Really nice stuff.
Thanks.
So you said you expect about 1% of O stars to be overcontact systems, but you didn't explain how that number rises. I mean, you said it should be relatively common, but that seems like a small number to me because there aren't many O stars around. Um, but doesn't that number depend very crucially on the lifetime of the overcontact phase and the assumptions you make about that?
Yes, exactly. Yeah. So I mean, this was work from Jan Hennekel. He did some population synthesis predictions, and he came up with this number of about 1% of the observable O-type stars should be contact, and about 3% should be semi-detached. It's actually interesting. I mean, I didn't really talk about this much here, but if you look at the statistics between the contacts and the semi-detached systems that we have, the ratios between the two of them seem to match, but the overall statistics compared to the broader sample don't really match so much. So indeed, yeah. I mean, there's, as I kind of mentioned, there's a lot of tuning that you can do with these evolutionary models. And that's just due to the fact that we don't have the observational constraints to say, hey, no, this parameter needs to be within this range. So yeah, I mean,
But as you pointed out, I mean, they're easy to find, right?
mhm.
I mean, they're easy to find. There can't
Yes.
be a huge error in the number.
Yep.
It must be more or less right. So this, as you say,
Yeah.
this indicates something fundamentally
Exactly.
that's understood about. Yeah. Okay.
Yeah. So I do think that there is, I think that there are probably more out there that we have missed, but I don't think we're going to increase that number to the 1% that models tell us to. So, I mean, this is kind of constraining. This is a constraint that we can use to kind of better understand the sample. Yeah.
There's another question.
Thank you very much, Michael. I actually have two questions. One is a very basic physics question. I'm sorry. You said that it's expected that the mass transfer leads to a Q of 1, basically, and that the mass usually transfers from the more massive to the less massive one. I might have missed this in my undergrad class, but why? Because my intuition tells me the more massive one has more gravitational force to pull, but I know it's not that way, but I just don't know why.
So for one thing, it should be evolving faster, right? So it should be evolving faster and expanding, which will cause it to push mass to the companion. If they're both the same mass, you expect them to be more or less evolving at the same rate. So, I mean, you may expect there to be some kind of, yeah, some kind of convergence towards a mass ratio.
Okay, so it's just the evolution. Okay, yeah,
Yeah.
that makes sense. And the second question in the diagram where you showed the path to the black hole mergers, there was a time scale written as basically it's 2 gigayears, right? 2,600 mega years. That would be like the time scale from the SAMS down to the black hole merger, or because it seemed like a very big time scale for massive stars.
No. So this is just from the time that the black hole binary is formed to the time that they merge. So this is just pretty much showing that if you have a 41 plus 41 black hole binary in a system or in a period of 3 days, that it'll take 2.6 gigayears for it to actually form a gravitational wave.
So many orders of magnitudes more than the progenitors evolved.
Yeah. I mean, for massive stars, you expect them to evolve on the millions of years.
Yeah, that's what I had in the like.
Yeah.
Okay, great. Thank you.
Yep, no problem.
Okay, another question here.
I think you said that when you have a black hole system and you have a third star, that would accelerate the merger. Why?
So when you have the triple companion, you have these lead-off Kozai. There's the Kozai lead-off mechanism, and what this does is this transfers angular momentum from the orbit of the triple between the orbit of the triple and the orbit of the binary. So what happens is that your triple orbit is processing out of the plane of the orbit of the binary system, and as it does that, it increases the eccentricity changes, and it ends up kind of through these pass-bys with the binary, sapping angular momentum away from the inner binary system. So it's just these kinds of triple interactions that could cause your inner system to lose angular momentum.
Quantitatively, will it make it 10 times faster? Or
It really depends on the exact parameters of your triple orbit. So I mean, the oscillation timescales, are sensitive to the neutral inclination, to the mass of the inner system versus the mass of the outer system, the distance between all of these things. So I mean, it's hard to put a specific number on that. But yes, it should speed things up to some degree if it's close enough. If it's not close enough, then effectively it's just a regular binary. So
Thank you for the very interesting talk. You showed on the HR diagram the kind of the red points and the blue points. So the kind of disentangling of the classical method. I think the acronym was GA, and then the spams. But really what you show in spams is that you treat this whole thing as one thing, like the whole surface, and you break it up into this mesh, right? So how do you, like, what is a star in spams? Like, how do you define how do you separate it into just 2 points?
yeah, so this is something that took us a while to kind of converge on how we were going to handle this. It is true. What do you call the temperature of a system whose temperature is varying across the entire surface? So the way that we kind of do this is we base it on the luminosity. So we say that your effective temperature is the total luminosity of your star using what is it? Sigma port. Yeah. I don't have the equation off the top of my head. So we base it off of that. So we can assign one effective temperature to the star, which is taking into account the entire surface of the star, not just an individual point on the surface. We do the same thing with the abundance and the log G and all of these other things. So we assign a surface averaged parameter, but what we are doing is we are accounting for all of these changes across the surface. It's just to kind of compare with models, because I mean,
Okay, I think there are 2 questions online. If you want to unmute and ask your question.
Hi, Michael. Really nice talk and really enlightening. I have 2 questions, and well, here's Paco. I don't know if you've seen that. Anyway, so I have 2 questions. One is just following the last one. I think most of your results also rely on your surface temperature distribution for each of these patches, which must come from some assumption from Phoebe or whatever binary, interaction code. So are there any physics missing for that could lead for you to get this difference, for instance, in the masses that you were getting?
So I didn't catch the last part. Is there physics that's
So
missing?
Is this any kind of physics in determining the temperature at each of these patches and the corresponding gravity, so that a different temperature distribution which will not account for whatever other processes could lead to a different profiles and a different interpretation of the systems?
For sure, yes. I can tell you right now that the distribution of temperature across the surface that we're using is wrong. The problem is that we don't have a better formalism yet. And I know that there are some groups that are working on this, more in the context of low mass contact binaries, but it should be applicable for high mass contact binaries as well. But yes, no, indeed. I mean, right now we're using the von Siepel gravity darkening prescription, which is just a simple relation between your temperature and your log G, an exponential relation. However, there are alternative gravity darkening methods that work well for example, rapidly rotating systems and for close binaries, but not contact systems. So the Espinosa-Lara gravity darkening prescription, for example, works for up until your systems come into contact. Unfortunately, they haven't extended this formalism to the contact phase yet, because of the fact that you have a common surface makes things much more difficult. So,
Yeah.
indeed, I can tell you right now that the surface temperature distribution is wrong. But yeah, until we come up with a better formalism, this is kind of the best that we can do. So it is
Yeah, I
possible
guess-
that this could change the picture. Yep.
Yeah, I guess if you have different systems with different F values, separations at the end, when you have a very low F value, that should converge to the traditional GA disentangling algorithm. And the other question I had is related to the abundances. I mean, I was a bit astonished to see that your carbon abundance, for instance, inferred from the GA approach was fitting much better with the expectations that you got from the SPAMS approach. So can you comment on that? Why did you get almost a DEX difference in the carbon abundance determination between both approaches?
Yes. So I had a backup slide on this, and I think I got rid of it. Yes. So when you account for the 3D geometry, or when you account for the temperature distribution across the surface, what ends up happening is that, if you give me 1 second, I can find the slide. Give me 1 second.
Yeah.
I'll find this because it'll be much easier to explain. You don't see my, okay, good. Pretty much what happens is that because of the distribution of temperature across your surface, the abundance that you would measure at different temperatures, or rather the equivalent width that of a specific abundance changes as a function of temperature. So if you look at your equivalent width of your carbon line at a given abundance at a temperature of 30,000 Kelvin, it's going to be different than if you look at the same set of carbon lines, if you look at their equivalent width at a temperature of 40,000 Kelvin. So because you have this distribution of temperature across the surface, what ends up happening is that you're averaging all of these equivalent widths, which changes the overall abundance that you would measure with 1D techniques. So I had a paper on this in 2023 where I looked at rapidly rotating stars, but it's the same kind of concept that applies for contact systems or semi-detached systems as well. That if you don't account for the temperature distribution across the surface, you also measure incorrect abundances. Now, why the abundance here is so much above the, I don't find the slide. I think that it's good enough, what I've said. Now, the fact that the abundance here is above kind of the, give it a sec to load, above the zero evolutionary track. I picked a bad example, to be honest. We have other ones where this is not the case, but this is something that we were confused about, and I don't remember what our conclusions were for this specific system. But yeah, it is something that we noticed, and it is something that yeah, caused us to second guess.
Okay, thanks.
Yep, no problem.
Yeah, okay, and there's one final question by Artemio.
Okay, thank you very much, Michael, for this very nice talk. I have a short comment and a question. The comment is simply that we do not find any evidence of chemically homogeneous evolution in other galaxies as well, coming from perhaps fast rotating stars. But in a very recent paper by Andreas Sander and colleagues, they find that the mixing and overshooting may be underestimated in evolutionary models. So the evidence is controversial here in any case. And the question is about the lack of equal mass systems that you detect. Couldn't you expect a strong observational bias? Because if you have two stars of the same mass, probably they have the same spectroscopic appearances. And then if the inclination is not favorable, then you don't expect to be able to see them as a binary, neither spectroscopically nor photometrically. Could that be correct?
So just based on the geometry, we can detect these systems down to very low inclinations. So even if they appear similar spectroscopically in terms of their spectroscopic features, the very high semi-amplitudes as well as the light curve variations themselves means that they should be detectable, even equal mass systems. So it's difficult to kind of get around that. I mean, you'd need to be below inclinations of below 10 degrees pretty much before you'd start being limited by that. As long as you're a little bit above that, you would still see the light curve variations. So it's possible, but I don't think that this would be a very large contributing factor. Like I don't
So
think
you
that
could discard this as an effect, actually.
yeah.
Okay, thanks.
And to your previous comment, that's very interesting. I know that there was one system that was suspected to be going through chemically homogeneous evolution from Gloria. I don't remember the exact telephone number of the system. But no, I mean yeah. I mean, with chemically homogeneous evolution, it was something that's been proposed, but we haven't really found the evidence for it quite yet. So I'm a little bit skeptical personally, but we'll see. Time will tell.
Okay, thank you very much.
Yep, thanks.
Okay, I think there's no time for any more questions, so we can thank the speaker.